Hi, my name is Sugwan, an undergraduate student from Seoul National University. I'm going to present our work course. The goal of course is to enable 3D human object interaction reasoning in a self-supervised way. Given a category keyword of an object as input, course aims to reason about the 3D HOI represented as probabilistic occupancy distribution. Course learns the occupancy distribution in canonicalized space, which can be used to infer object distribution for humans in any pose. Course can also infer possible distributions for various semantic types of HOI, where semantics can be given as natural language description or optionally can be further specified with body parts. Humans interact with objects in specific ways. For example, we wear hats on our heads, ride a bike holding handles and stepping on the pedals. While this is known to us, it becomes challenging when teaching to machines, as providing supervision with 3D HOI annotation can be hard to scale due to numerous variations. Alternative approach can be leveraging 2D images from the internet, as they are scalable and easy to get. However, the method becomes ambiguous when learning 3D, as they do not contain explicit 3D annotations. Also, anonymously collecting 2D images can return the images without HOI, which will hinder the quality of the results. Our intuition is that we can mitigate this problem by synthesizing 2D images of HOI and use humans as cues for conveying 3D spatial relationships from 2D knowledge. The key challenge then is how to synthesize 2D data regarding semantics of HOI and how to unify 2D spatial knowledge into every 3D space of post-human. Course tackles each challenge in two phases. The first phase, the dataset generation phase, starts by generating prompts that describes the semantics of the HOI and creating a database of multi-viewpoint images from the HOI prompt using diffusion models. The second phase is the aggregation phase, where we extract 2D cues from the images and aggregate them to 3D canonical space. By cleverly selecting the images to aggregate, we can infer distribution per semantic type of HOI. Let's dive into details. Given a category keyword, we use large language models to generate prompts that describe plausible HOI, which allows us to represent much more diverse and open set of interactions than action categories. Using a set of generated prompts, Course leverages text conditional diffusion model to create an image database. We then apply keypoint-based filtering to remove images that contain erroneous humans, which are unsuitable for HOI learning. Consequently, we predict 3D humans from the images. Using the 3D humans, we calibrate the camera for the generated image by using humans as anchors. Course utilizes object segmentation as 2D spatial cues, which are aggregated to human-centric 3D space using disambiguated cameras. However, naive aggregation of 2D cues will lead to dispersed accumulation and cause high variance due to remaining pose diversity. Thus, Course chooses to aggregate 2D cues in post-canonicalized space to assure coherency between rays. By canonicalization, we can also learn post-conditional distribution. By cleverly selecting the images to aggregate, we can infer the distribution per semantics of HOI type. Here are a few example results for various categories of our method. To note again, the high values denote the high probability of object occupancy. Here are semantically clustered results. See the surfboard example. While the distribution for the balance shows a mode below the feet, the distribution for carry exhibit mode around torso and arms, which is a part used for carrying a surfboard. An interesting example is also shown for the category bicycle. For the prompt standing next to a bicycle, we can see a donut-shaped distribution. Thinking that a person can head any direction while standing next to a bicycle, we can expect a rotationally invariant distribution, a donut shape. Course is novel, thus provides opportunity for myriads of applications. Here's an example, single image HOI reconstruction. Given an image, we apply instant segmentation to find the main object category, where we can apply course as prior to infer the object distribution. We apply threshold to run margin cubes and get the object mesh. Our method does not require any template mesh. Thank you for listening.